Okay. All right. Welcome, everyone. Uh, so, just as we've mentioned from before, ang agenda natin for our ILW, at least for the first part, for your Monday class, quote-unquote Monday class, is that we discuss some problems from problem set 3 and problem set 4 for your upcoming exam, your quiz 2. Right? So, ayan. And we will be talking about problems 1, 5, and 8 for problem set 3. And we will be talking about problems 5, 8, 10, and 11. Additional na yung 11 for your problem set 4. Okay? So let's start off with this problem. Problem set 3, number 1. A closed system containing a fluid undergoes quite a number of processes where two of the three values of the system's energy are explicitly known. So as you can see here, right? As you can see here, meron tayong mga dalawang black and isang red, right? So that will be that will serve as your answer. So because I'm looking at the answered version already, which should be available to you guys by now, right? Also, it is known that the processes loop back on each other. The last process will take the fluid back to its first state. So as you can see, the process here, the first column, will contain the different initial and final states, right? From 1 to 2, 2 to 3, blah, 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 up until 7 to 8, and then 8 goes back to 1. This is known as what we call a thermodynamic cycle, and this will be the basis for your final topics for the term. So for you guys, right? For you guys, that will be your the coverage of your final examination. Meanwhile, for the MEC-Eng people, that will be their coverage for quiz 3 because their final examination will contain everything. Okay? So please fill in the missing values through the application of the first law of thermodynamics. So something like this, right? And then let's just fill in these values. How do we even know what's going on? All of them seem positive, which means it's a bit weird because I taught you guys the sign convention, but we can see there are different key phrases here with the numbers, so that gives us an idea of, oh, what exactly do we need to get, right? Or what exactly these values, these numbers mean, okay? So once you've inspected, once you've done the complete table, once you've filled out all of the values, what do you notice that's special between heat and work? We'll talk about that later, right? So for now, let's just go ahead and go immediately into this this space, right? Ito lang yung kinopya ko. This is the only thing I copied just so we don't have the awkward phase where I keep going alt-tab back and forth, right? So now I've copied everything here. And what we are supposed to do is we are supposed to dissect the different words in here, right? So that we can properly answer what's in here, right? Or what's in here and so on and so forth, right? So, ang sabi ko, as I've told you guys before, the crux of your problem set 3 and basically your topic 3 and the entirety of your quiz 2 depends on what we call the first law of thermodynamics, right? Basically, if you can include this in your solution, Q minus W equals delta KE plus delta PE plus, in this case, we are talking about a closed system. So we will be talking about change in internal energy U, right? If you can write that down, that already means that you have partial points, right? And so now, in this case, there is no mention of whatever changes in speed or velocity, so we can remove the fact that KE, your kinetic energy or the fluid's energy, might change, and there's no mention in a change of altitude, no nothing like that. So there's no gravitational potential energy either. So what we will be left with is something like this, right? Q minus W is equal to your change in U. And this is the operative formula for everything in here, actually. If anything, you will just be doing this over and over and over again, right? But now, you might just think that, oh, it's just this equals this, right? But of course, there are these key phrases that we need to watch out for as well, right? Ang kailangan mangyari for every process, right? For every process, there needs to be a before and an after, right? So if we imagine this thing going before, right? This thing going before, and this thing going after, right? Your heat, right? Your heat will be positive if it goes in, right? Your heat will be positive if it goes in, aka going in, right? That's the operative word for heat going in. That's positive. Right? And then if it's going out, of course, the reverse would be heat going out, right? Heat going out. Now this is reversed for work, right? For work, or how I like to think about it, electricity or energy. That's why I have this thunderbolt shape instead. If your work is going in, quote unquote going in, it's negative actually, right? What does this mean? Of course, there are different phrases for work now. It's either being done on or done by. Done on by who? We're talking about the system here. System work. So it's being done on the system. It's being done by the system. If you are giving work, if you are giving electricity, that means you are you, not the system. If you are giving the system work, then work is being done on the system, right? Work is being done on the system, right? But notice the work is going in, right? So that's a bit weird because baligtad, right? It's opposite. Wait, this is negative, but it's going in, right? And therefore, conversely, if your system is the one doing the work, right? Being done by the system, the work is being done by the system on something else, it's positive, right? It's being done by, right? And this confusion can be settled because of the fact that you have a negative sign in here, right? In your first law of thermodynamics, what happens is that you are always thinking about the negative sign, right? What happens is that if you apply the negative sign and then the sign convention for your work, for example, what happens is that if we just say positive work, what does positive work mean again? It's being done by the system. Look what happens, positive times negative, meaning negative, meaning leaving, meaning where does the work being done by the system come from? It comes from the system itself. So if they are imparting, if they are giving away work, they are losing work. Look, the direction is outward, right? The system is giving away its energy to something else, right? Meanwhile, if what happens is negative of negative work, which means the system is being work is being done on the system. There you go. Work is being done on the system. You will see negative times negative is equal to positive. Positive, it's entering the system now. Work is being added to the system, right? Although we don't think about it that way, work added to the system, we say that it's being done on the system. Though the system is the recipient, right? The recipient. In here, the system is the recipient, right? In here naman, the work is being done by the system. The system is the one giving out the energy, right? So in this case, it's leaving. It's gonna be a negative number. So enough of the theoretical. Let's start by actually trying the first, right? The first few ones, right? Going in. So in my head, this is my thought process, In my head, what's happening is something like this. I think about a system. Usually it's a box or just like a squiggle. 1,000 somethings in the original problem set. It's in kilojoules, right? 1,000 kilojoules of heat is going in. I'm not even going to bother writing down the units. Why? Because, well, it's all in kilojoules, right? I don't have to worry about anything, right? And then 3,250 work is being done on the system. Done on the system, not done by the system. The system is the recipient, so it will get more energy. Look what happens. May papasok na 1,000, may papasok na 3,250. Therefore, in total, the amount of energy it receives is positive 4,250, right? Positive 4,250. And of course, because it's positive, right? There's a change in stored energy. The positive has a connotation that it should be higher, right? Higher. And indeed, that is the answer. 4,250 higher, right? So this is what happens in my head. Like literally, that is what happens in my head, right? And if you have your calculator with you, in case that your your mental math skills aren't that fast, di okay lang. Don't worry, right? Absolutely don't worry. Right? Now, this is where things get a little bit rougher, right? The second one, process 2 to 3, right? Now, you know that the system has work being done by, the system is doing some work, right? Done by the system, right? Done by the system, meaning the system is giving away the work, 1,370 worth. But you know that all in all, it should be lower, right? The change in the stored energy of the system is 4,140 lower. But this is not all of it, right? There is still a value of heat. Now, for you to be able to give out 4,140 worth of energy, should your heat come in or come out? Syempre, for us, we can see that kind of we can see that kind of happen in real time for our thoughts. Of course, more energy should come out, right? But by how much? Right? By how much? By 4,140 minus 1,370, which gives us your 2,770 going out. Going out. And just like that, there you go, 2,770. And mind you, I'm not even touching this yet. But here we go. Ito na nga, right? If you don't want to deal with this kind of thought process, that's okay with me, right? We think differently. We're different people. Don't worry about it, right? The thing is that this kind of thinking and Q minus W is equal to delta U, that is the same, right? That is the same. What I'm doing here is I'm turning it a bit more tangible because, mathematical equations have the risk, right? Have the risk that it doesn't seem real. Like, ano ba yung kino-compute ko? What am I computing here? Right? What am I computing here? This is just a blob and like some arrows are coming out and in, whatever, right? So now once you confirm, this much energy, which is 4,140, this much energy is coming out of the system. Okay, so everything is okay. Right? Now, if you want to speed things up, undoubtedly, you're going to have to use the first law talaga. Right? 4,390 going in for the next process, and we know that 7,510 higher is the total result. Therefore, right, you know that 4,390 worth of heat is coming in, right? And then the result should be that it's 7,510 higher, positive, right? Therefore, you can just solve for your value of W. In this case, you can shift solve, right? I hope you guys don't use shift solve for something like this. Hopefully you can transpose this in your mind, right? Transpose. We will have 4,390 minus 7,510. That will be, your work is negative 3,120. But I am not trying, 3,120. I am not allowing negative numbers here. Right? Look, all of them are positive. Look, it's just the phrases that are different. If you mean negative work, that means that from here, right, it's being done on the system. The system is the recipient of the energy, the recipient of the work. Therefore, your answer here should be 3,120 done on the system. Right? Look at this. It's going in. It's being done on the system. So positive, positive. That would result in your net 7,510 higher. Right? And you can actually make this just, algorithmic. Right? The thing about some processes or just some thought processes is that after a while, you just get used to it. Right? And in this case nga, the most important skill for this quiz is to get used to the fact of the conservation of energy or the first law, right? And the thing about this is that I believe it's somewhat natural for us. Somewhat natural. Like for this one, process 4 to 5, you know that nothing will change. Nothing will change. Okay. So if nothing will change, it should be 0. If nothing changes, then look what happens. You can just flip them and you can see that your Q is equal to W. Oh, very interesting, right? Very interesting. So in that case, if this is being done by the system, right, that is a positive kind of work, right? Done by the system, right? So ibig sabihin, this should also be corresponding to a positive value of your heat. What is a positive heat that's going in? 2450 going in. Right? As you can see, this goes into the system and then the system is giving away work. Therefore, it's a break-even, kumbaga, right? It's a break-even, you're giving some and you're getting some, right? And those two things are the same number, so you get nothing in return, right? All in all. Now, again, we repeat, right? 2,100 going out. Try and imagine 2,100 going out and then 4,120 being done by. What is the direction there? It's being done by the system. That means you're giving away more energy. So what are you going to do with these two numbers? Are you going to add or subtract? Right? Of course, you're going to add because they are in the same direction. They are both going out. Therefore, your answer here should be 6,220 lower. Because you're giving out both, you should be going lower. Let me see. I don't trust my 6,220 lower. There you go. I don't trust my mental. Right now, again, going out, 2,820 going out. And then as a result, 1,100 goes lower, right? Your system loses a net of 1,100. Wait a second. I gave out more than this. That means that I have to receive some. I have to receive some energy back such that the net would be I don't lose this much energy, right? And so actually, I'm not even looking at anymore, right? I'm not even looking at the first law anymore. I'm just thinking about this in terms of going out, going in. Hopefully, you guys understand when you were in that class. I don't remember when that was, but I told you guys we were accountants. We are accountants in this case, right? You have to account for the flow of energy. 2,820 minus 1,100. You need to receive... right? You need to receive 1,720 amount, that much worth of energy. If we're talking about work, this should be done on the system so that we can receive this much energy. If we are giving away 2,820 worth of heat, we need to receive 1,720 worth of work such that our net is 1,100 lower, just lower. So if we again do this in terms of the first law, we will get 2,820 negative minus done on, right, negative 1,720. And if we do this calculation, this should give us negative 1,100, right? And then we just finally do some of these left. 3,960 going in, so you receive energy. 2,820 done on, you receive more energy. Therefore, you should just add these two numbers, right? So that will give you 6,780 higher, right? You're receiving heat and you're receiving work. So in terms of that, you should get even higher. Yeah, 6780 higher. And then finally, for our state 8 to state 1, you know that the net value is going lower by 7080. You also know that you are giving away, done by the system, right? You also know you're giving away 5850 worth of energy, right? Wait lang. I'm not giving away enough energy so that I can get to the 7080 value. I need to give away more energy, right? How much more energy? Well, 7080 minus 5850, that would give you 1230. You need to give this away pa. So going out. Right? So again, if you do this in terms of your first law, what you should do is negative 1230, or rather, we don't know the value of Q. So Q minus done by, so negative 5850 is equal to, oh, sorry, done by pala. So that's positive, right? Positive 5850 is equal to lower, right? Negative 7080. So if you transpose, you will get your value of negative 1230 or 1230 going out, right? This is our filled up chart, or table pala rather, table, right? And the thing about this now is that, yes, there you go, right? But now we go on to this part. Inspect the completed table. What do you notice that's special between heat and work? What is also special with the change in stored energy? Now, a lot of people here have answered in their submissions that Q minus W is equal to delta U. And for me, that's on me because I haven't specified what exactly besides the first law is so special about this, right? Yes, indeed, heat minus work is equal to change in stored energy. Yes, we just discussed that, right? That is the core of our discussion. Now, what I wanted to ask people instead was that, what do you notice with this chart, right? What do you notice with this chart? Hopefully, once you do some experimentation yourself, you can see that if you sum up all of the heats and all of the works, right? If you sum up all of the heats and all of the works, what happens? Right? Kaya siya naka-table. This is why I've organized it in this table so that maybe the columns and the rows are supposed to give you something, right? Something. And indeed, if you go row by row, you can apply the first law for a process. The first law of thermodynamics for a process, right? In this case, if you do decide to do your due diligence, right? You see, right? Let's just compute the values of Q here. Oh my goodness. Bawal ba? I can't do that. Oh man. Okay. Sige. Fine. I'll just do this on my calculator then. Right? I'll just do this on my calculator. 1,000 going in, that's positive 1,000. 2,770 going out, minus 2,770. We'll just keep going. Plus 4,390. Plus 2,450. Minus 2,100. Minus 2,820. Excuse me. Plus 3,960. Minus 1,230. That will give us a total of 2,880. Right? So your total Q is 2,880 kilojoules. Right? And if we also do this for our works, note again, done on the system is negative, apparently, and then done by the system is positive. Right? So minus 3,250 plus 1,370 minus 3,120 plus, right, done by, no? 2,450 plus 4,120 minus 1,720 done on, tama, minus 2,820 plus 5,850, you should also get a value of 2,880, which is very interesting, right? And if you do this, if you do decide to do this for other thermodynamic cycles, you will always see that these two are the same. Therefore, your total heat is equal to your total work, right? I will discuss this in more detail why this works for a thermodynamic cycle and only for thermodynamic cycles. This is not a coincidence for a thermodynamic cycle. If right, if this happens for a string, a series of processes, that's a coincidence. But if you know that the string of processes is a thermodynamic cycle, that means that this will always be true. Okay? Now, right? What else can we do? Well, let's look at this. What if we sum up all of the changes in stored energy, right? Let's try this now. 4,250, 4,250 minus, kasi lower, right? Because it's lower, it's negative 4,140 plus 7,510 plus 0 minus 6,220 minus 1,100 plus 6,780 minus 7,080, and you will get, very interestingly, your sum, sigma, of the changes in your stored energy is 0, right? Also, there you go. These are supposed to be your two conclusions for letter I, for the last part, right? So this is a bit weird. This is very intimidating, right? The sum of the changes, right? So hopefully you give that some time to process, because that will be the crux of our discussion when it comes to the latter part of the term, right? Which is about cycles, right? So that is hopefully what I was asking you guys to do, right? And hopefully you also have gained somewhat of a more tangible kind of intuition for the first law, right? For the first law. Okay, now we move on to number 5, right? We move on to number 5, which states sometimes we don't even know much about the process. All we know is what we can measure, right? I'm talking here about just any process in general. Barometers and calculations report that the pressure and volume for the initial and final states of a closed system filled with a fluid are P1, V1, P2, and V2 respectively, right? So P1 initial pressure, P2 final pressure, V1 initial volume, V2 final pressure. Using these 4 variables, and I mean to say variables because they will change, what would be the formula for the process's polytropic index? How will this work? Right? Supposing that the process is indeed, right? Supposing that the process here, right? Let's say given, right? Given values of P1, V1, P2, and V2, assume the process is polytropic. The process is polytropic, right? What we want apparently is a formula for the value of n, right? Formula of a value of n, right? As a function of these 4. 1, 2, 3, 4, right? This is very daunting, right? It's very intimidating for the people who are not very well versed with mathematical language. But basically, I'm just saying here that your n, the thing that I want, is just a formula. And it's a formula or a function using these 4 variables, right? Same thing as, I don't know, if you guys are programmers, hopefully in the MEM department, like there is some sufficient knowledge as to the use of functions in programming, right? I'm basically just calling upon, or rather I'm inputting 4 variables so that my output is this letter n, the polytropic index. So now my solution, or our solution, should be as follows. How do you even relate these 4 together? All I know is that the process is polytropic, right? So in a polytropic process, that is horrible handwriting. in a polytropic process, all we know is that PV raised to N is a constant, right? And the thing is, yun nga, a lot of the people struggle with this kind of concept, or with this kind of writing down the formula, right? So I immediately connect this together. If you have an initial and a final state in the process, that means that this value for both the initial and the final state should remain constant. Actually, as it travels, for example, this is state 1 and this is state 2. All throughout the process, this value of PV raised to N must be the same. That is why we can trace out this line, because this line is the collection of all the points that follow this process, right? It's the collection of all the points that follow this constant pala rather. And so now, what does that mean? Basically, if we take the PV raised to N of the initial state of state 1, that should be equal to a constant. Okay, some constant. I don't know what the constant is. So actually, there's 1, 2, 3, 4, 5, 6 things that we don't know. Right? So it's very intimidating for a lot of people who are not very confident with their math skills. But I want to remove one of them by saying that, oh, by the way, your final state, right? Your final state should also equal this same constant. Wait lang. A is equal to B. C is equal to B. Hey, what can we say after this, right? The transitive law applies. A is equal to C. Right? A is equal to C. Therefore, these two things must be the same as well. And so actually, you don't need to care about finding that constant value. All you have to care about is the fact that these two need to be the same. In this case, now you can just say P1 V1 raised to N is equal to P2 V2 raised to N. And as a result, now I will just highlight the value of N for us here. There you go. And now our goal is to solve that value of N, is for us to isolate this at the very least, right? What we want is just the value of N is equal to some function, right? We don't need to know the values of P1, V1, P2, V2. All we need to know is that we need to isolate this letter N. But the big problem is that it's in the exponent. So a lot of people, again, who are not that well versed in this kind of mathematical algebraic manipulation, is that they just go straight to shift solve. The problem with shift solve is that, the good thing with shift solve is that it can solve a lot of things. However, you'll get a lot of anxiety in the first place, right? Because it solves so slow and you aren't even sure if it will solve. Sometimes it just says, can't solve, sorry. Maybe you put something in wrong, right? Maybe there really is no solution. Maybe it's maybe it's isometric, right? If we recall, right? Recall. If your process is isometric, what is your polytropic index? It's infinity. I don't know how that would work, right? So now, how are we going to do this, right? The best way to counter, or if you see that your, if your variable, the one that you want to solve, is in the exponent, what you should do is remove the exponent. How do you remove the exponent from something, right? That's a bit weird to think about. Well, you apply a logarithm, right? You apply a logarithm because exponentiation and logarithms, right? Taking the logarithms are inverse, right? And I don't want to go through all of the details here, but we should recall, right? We should recall these two facts, right? These two mathematical facts. And I am going to a bit of calculus. So if you're taking Caling 1 or something, this should jog your memory as well. Pero this remains true everywhere, right? If ever you have E, right? If you guys remember E, right? That's the numbers, say 2, 7, 1, 8, 2, 8, 1, 8, blah, 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 right? If this number were raised to ln of something, it's like these two cancel out. And you are going to be left with that same number, right? The same way, if you see ln of e raised to a, it's like these two things cancel out. And you will be left with the same thing, right? And so now, I don't see an e in here. That's fine. It's okay, right? If you now have something like v1 raised to n, if you take the logarithm, right, the natural logarithm in this case, because this very what do you call this, it's very common for us to look at things in cases of in application of ln instead of any log, right? What you're going to see is that there's this superpower that logarithms do. If ever you have ln of something raised to an exponent, what the ln does is that it will take that exponent and shove it outside, right? This is the same thing as b ln a, right? That is what happens, okay? And so now, if we take the logarithm on both sides, right? If we take the logarithm on both sides, ln of p1 v1 n is equal to ln p2 v2 n, right? What will happen is something like this. Oh, I haven't even bothered to introduce this yet. Also, you will see that this is the product of two things, right? Of two terms, p2 and v2 raised to n. So if ever you do have two things that are multiplied, what you can do is you can split apart the ln. Another one of the superpowers of the logarithm, right, is you can split them apart with ln a plus ln of b. Conversely, if you see them split apart by a division sign, right, ln a over b, what you can do is split them apart, ln a minus ln b. Why negative? It has something to do with the fact that you can say that this is just a b raised to negative 1. And then this is the same thing as ln of a plus ln of b raised to negative 1. But wait a second, we just said that the superpower of the logarithm is to shove the exponent down. And so what will happen is that this will become negative. That is the one of the ways you can restate this kind of rule, right? And so what will happen here is that we will see ln of p1 plus ln of v1 raised to n is equal to ln of p2 plus ln of v2 raised to n. And so now we apply the superpower of the logarithm. We will say that now this is going to be ln of p1 plus n, right? And ln of v1 is equal to ln of p2, right, plus n ln of v2. And so now you can do the same thing you have done before, because now, yes, this is algebraic. I can isolate, right? I can isolate everything. So let's just move all of the n's to one side, to this left side, and let's move all of the things without the n on the other side, on the right side. So now what will happen is that we will have n ln v1 minus n ln v2 is equal to ln p2 minus ln p1. So now you can group these two together. You can remove the common n, right? So what you will see is that n times ln v1 minus ln v2 is equal to blah, blah, blah. And now you can put this all together. You can just divide both sides by this value. You will get your n is equal to ln p2 minus p1, ln minus ln p1 all over ln v1 minus ln V2. I can accept this. But why is my answer like this? Because you can apply the same thing that we have done before here the other way around. Right? You can apply the other way around. So therefore, what you can do is you can say ln of, you can absorb them into one logarithm. You can say P2 minus P1. And then you can also say that ln V1 over V2 works. Right? And so that is our answer. That is our answer. Now, the eagle-eyed among you will say, wait a second. Those are different, right? This is ln P2 over P1 all over ln V1 over V2. This is ln P1 over P2 over ln V2 over V1. Now, I will challenge you guys, or just, give you this exercise on your own to do. Are they the same? How did I get that other value? Right? So it has to do, if ever, you might want to look up the laws of logarithms, right? Laws of logarithms tayo. Or maybe you can choose to do this thing another way, right? Hopefully you guys immediately see what other thing I can do here, right? For this yellow part of the solution, for the last part. So ayun, right? This is going to be correct though. I can still attest this is correct, right? And so now we will go to your number 8. Right? We will go to your number 8. And please, if there are any questions, just go ahead and message me. Okay? Go ahead and message me. Right? That's going to be our answer for number 5. Now, number 8 tayo. Number 8. Okay. Right? Full disclosure, this is not my creation. This is a creation of Sir Neil Lopez. He used to be, I don't know, he used to be a professor of the mechanical engineering department, and I don't know if he taught thermal sciences na. All I know is that he did teach thermodynamics for mech-eng people and also for IE people, industrial engineering, because as you can see, right, the in-out kind of mindset is also very useful for industrial engineers, right? But for now, yun lang, enough context, right? This is his creation. I just reworded it a little bit, right? And now, let's begin. A closed vessel made of a rigid material. Can we highlight here? I don't think we can highlight here. I'm going to open this in Adobe Acrobat just so we can see it being highlighted so that I can problem set 3. Ito na lang. Open with. Yeah. Yeah, there you go. So that we can highlight. Right? The same thing that we do in class. Spelling errors. Do I have spelling errors? Okay. Now, closed vessel. So immediately closed. Right? Right? Closed. A closed vessel made of a rigid material. Right? Immediately they tell us, right? I.e., in other words, will neither expand nor contract. That is already a big clue, right? Contains a volume of 0.5 cubic meters, right? This is going to be, let's just say this is blue, right? A volume of 0.5 cubic meters, because this is, what do you call this? A number, is placed on a stove. A stove. Okay, another keyword here is a stove, because, well, you're probably going to heat, right? You're probably going to heat it. It is known that the container, right, initially maintained a two-phase mixture, initially maintained a two-phase mixture of water that is half dry. A two-phase mixture of water that is half dry. That is already a number for us, although it's not clear yet, but it's half dry. 50% dry at 1 bar. Okay, at 1 bar. It's also another number, right? Is this same? Okay. After heating, so this is now, right? After heating, the barometer measures a final pressure of 1.5 bar, right? This is gonna be a number. Now, The question is, what are the initial and final temperatures of this sample in degrees Celsius? How much water vapor is in the sample in the initial and final states in kilograms? And if we were to continue the heating process until the sample is fully dry, in other words, is just full of steam, how much pressure would the gauge read then in kilopascals? Okay? So not a lot of numbers here. In fact, there's only 1, 2, 3, 4, right? 1, 2, 3, 4 pieces of given information that are numerical, right? And 1 isn't even like a number. It's just half dry, right? That's all we can get. But this is enough information for us to completely solve this problem, right? Now, let's try to actually visualize, right? Let's try to visualize number 8. We have here a rigid vessel, a closed rigid vessel. Let's just say it's a drum that's welded, right? A drum that's welded, not that big. A drum that's welded. And this contains water, right? Water. Oh, right. Sorry, yes. There you go. Two-phase mixture of water. Should be highlighted as well, right? Water ang pinag-uusapan natin. We are referring to water as a substance, therefore probably it's a good idea, it's a good time for us to just head into our tables, okay? Sabi daw, this is of a rigid material. They say this is rigid, therefore this will not expand nor contract. That is the operative term. This, when you see the word rigid or whenever they tell you that it will not expand nor contract, that is already a very good term for us to say that this thing is going to be an isometric process, right? This thing will undergo an isometric process, period. Right? So, lagay tayo. Given. Right? Given. So, this is going to be an isometric process. Very interesting to learn, right? So, rigid, isometric. Okay? And if the volume is constant, and mind you, this is a closed system, right? This is a closed system, just so we're being clear, right? The mass should also not change. If the volume is constant and the mass is constant, therefore, volume over mass should also be constant. What is volume over mass? That is specific volume. Specific volume. And so whenever something is isometric, you should also know that not only does the volume remain constant, but also the specific volume. Just so we're being absolutely clear. Because you guys might misconstrue this, or in some cases, you won't even think about it. The V is constant, therefore the V, small v, is also constant. Right? Contains a volume of 0.5 cubic meters. Therefore, the volume down here is going to be 0.5 cubic meters. Okay? It's placed on a stove. Okay. So, we'll place it on a stove. Right? And now, this stove is going to heat. Probably. Right? Is going to heat. Ayun, after heating bala. Right? There you go. That's the operative phrase. Heating. So, the stove will impart some heat. Okay? Until the barometer measures the final pressure. But first, let's take into account the initial state. Initially maintain a two-phase mixture of water. That is another term for saturated. Right? Saturated water. That is half dry. So for state 1, all we know is that it is half dry. AKA, the the quality is 1/2. Right? And the pressure apparently is 1 bar. Okay? After heating, right, state 2, the pressure is determined to be 1.5 bar. Right? And mind you, again, V1 and V2 will both be the same at 0.5 cubic meters. Okay? And so, what they want from us now is, I suppose, the required. Letter A, what they want from us is the initial and final temperature. So T1 and then T2. And then letter B. What are the, how much water vapor is in the sample in the initial and final states. So you can treat this, you can say this as m vap or m vapor at state 1, right? And then m vapor state 2. Or if you're being very particular, mg1 and mg2, because this is vapor we're talking about, right? This is the gaseous state, right? Letter G instead of letter F on the left side. Ewan ko if nami-mirror yung camera ko. Wait lang, let me see. Left. Oh, sorry. So baligtad pala. It's being mirrored, right? All right. You guys know what I'm talking about, right? So let's just make this vapor MV1 and then MV2. And then finally letter C. Oops. If we were to continue the heating process until the sample is fully dry, how much pressure would the gauge read then? AKA a pressure 3 such that it's fully dry. What does dryness mean? That just means it's full quality, full 100% steam, right? This is now all we are given, so this should be enough, right? Now, for states 1 and 2. For states 1 and 2, how are we going to know? Well, we know for state 1 that is saturated, right? Our solution will be as follows. Let's just drop down here. We know that state 1 is saturated, right? State 1 is saturated because of the appearance of, right? Because of state 1's quality, which is half dry. How can you have quality? Only when you are saturated, right? So therefore, we already know the temperature, right? We already know, therefore, right? This is because, and this is therefore, T1 is the Tsat, is the saturation temperature at P, right? What? P1, which is 1 bar, right? If we know it's saturated, we know that your pressure and your temperature are intercoupled, interconnected or intermingled. Basta that kind of concept, right? Therefore, we should just go to table A3. This is the properties of saturated water at a certain pressure. And if you look at the bar here, right, that's 1 bar, it corresponds to a saturation temperature of 99.63 degrees Celsius. Therefore, your T1 is 99.63 degrees Celsius. Immediately, you have an answer for state 1. So let's just add this here. 99.63 degrees Celsius. Now, right? Now, what else? Right? What else? I don't know. Right? What about state 2? Do we know the state of state 2? Well, not yet. Sorry, I only have one piece of information here. But you should also be aware that actually you have 2 pieces of information already. We just haven't thought about it yet. Yeah, wait, hold on. Okay, I've adjusted my electric fan. Hopefully that's not heard. Let me just check my... Okay, it's not being heard. All right, good. Now we actually have 2 pieces of information. Actually, we also have V1 and V2, right? V1, big V1, which is 0.5 meter cubed, and also V2. The problem here is that, well, I don't know how to use that, right? That's not in the table. That's not nothing. I don't know what these 2 values would represent, or rather where these 2 values would fall under. All I would know, or rather what would be more useful for me, is that if I knew the specific volume instead, right? That would be nice. But actually, since state 1 is fully defined by these 2 pieces of information, I should be able to also determine your small v1 and your small v2, your specific volume for state 1 and your specific volume for state 2. Okay, right? To know state 2, right? Oops. We must know we must know V1, which is also equal to your V2, right? We just proved that a bit earlier, right? We just proved that a bit earlier. Therefore, what is your V1 going to be? Because it is saturated, it's going to be VF plus X1 times VG minus VF, right? And as a result, because we know, right, because we know that it is saturated, right, in this saturation region, we can nab the values of VF and VG, right? The value of VF in this case is going to be 1.0432. And then mind you again, right? Always just look at this. This is times 10 raised to 3. In this case, right, the tables are helping you out directly. They're asking you, please, when you use this value, divide it by 1,000 first. Meter cube per kilogram. And then your VG is 1.694. 1.694 cubic meters per kilogram. As a result, we can just plug this all in because we have values of this, and this. We can get your V1. Therefore, when you get your V1, it's going to be equal to 1.0432 over 1,000 plus 0.5 times 1.694 minus 1.0432 over 1,000. Now, when we get this value, 1.0432, 1,000 plus 0.5 times 1.694, 4032, 1,000, you will get the value of, right? You will get the value of 0.8475 meter cube per kilogram. I will choose to do this because I want a bit more accuracy than just like two decimal places. I recommend going 4 or even 6 for specific volume, but this is good, right? And now I will share with you, if ever you are watching this video, a kind of a trick. It's not really a trick, pero it might be useful for you if you barely have enough time. There's an approximation here. And this is very engineering. This is a very engineering thing to do. Look at this value. If you actually look at this value, you will say that, wait. If I can just put the decimal place 1, 2, 3, why 3? Because 1,000 has 3 zeros, right? If you just put the value, if you put the decimal place in the correct value, this will be 0.0010432. What is the next thing you say to yourself? That's really small. What happens is that sometimes you can just say that's 0. Right? You can just say that's 0. And this is very, very scary because you are dealing with the fact that if your VF is equal to 0, look at what the density is. Your density is just 1 over VF. Look at what happens. It's infinity, So it's kind of weird. The density of water is not infinity, but for the purposes of this discussion in this problem, whenever you're dealing with the density of whenever you're dealing with a specific volume of liquid water, what you can do is just say it's 0. I will put this in a different color, right? Approx, right? Approx. When dealing with liquid water, right? When dealing with liquid water, try VF is equal to 0. Right? Let's try this. If your V1 is just going to be VF plus X1 times VG minus VF, and if you're dealing with water, cancel. That will give you X1 times VG. In this case, let's try this out. 0.5 times 1.694 will give us the value of, I don't like this. 1.694. That will give us a value of, look at that, 0.847. You won't even notice unless you go, what, like 4 decimal places, right? It's very scary, right? That 0.0005 is the only thing that changes when you are dealing with this thing, because again, you're dealing with such a small value of VF, right? So in this case, I will still try to do this. I will still try to do this problem with the 0.8475 because that is the value that is actual. But we will see how things change, okay? Right? I will still bring this orange value with me. And now let's go to the next part of the problem. We know that this thing is also your value for V2. And moreover, right? And moreover, that this V1, V2 is just your specific volume in general, right? The thing is, this will not change. This is an isometric process that we are undergoing. Therefore, I can actually change these now into something more useful for us. V1 is 0.8475 meter cube per kilogram. And V2 is now also 0.8475 meter cube per kilogram. Now, we have these two pieces of information. Finally, we can know the state of state 2. We can go to table A3, right? We have a pressure, so we go to 1.5 bar this time. Now, I will ask you, right? Now, I will ask you, where does that 0.8475 value go? Where does that fall under? Is it smaller than this? Or bigger than this? Is it in the middle of these two? And again, the temptation would be to say, no, it's smaller than this, smaller than 1.0528. But again, this is raised to 3. This is multiplied to 1,000. For you to be able to get the actual value here, right? This is a common pitfall, right? What needs to happen is that you need to apply the divide by 1,000, right? At P2, which is 1.5 bar, right? Your value of VF is actually 1.0528 all over 1,000. So the value is actually 0.0010528 meter cube per kilogram. Meanwhile, your VG is what again? 1.159 meter cube per kilogram. Now, we can see, right? We can see the actual value, right? Now, if you have this kind of thing again, if you have this, your value of VF, right? Which is 0.0010528, right? And if you have your value of VG, right, which is 1.159, where does this value of 0.8475 fall under? Of course, it's going to fall under the middle, somewhere in the middle, right? Somewhere here. Here? Yeah. There you go. This 0.8475, this is in the middle. Therefore, we know that state 2, right, is also saturated. State 2 is also saturated. And therefore, we can know now the value of T2, right? Therefore, the value, thus, T2 is just your Tsat again, once more, at your P2, which is 1.5 bar. Now, we can just get this from the table immediately and get your answer. T2 is 111.4 degrees Celsius. Okay, there you go. And now we have solved letter A. Very good. Now, what about letter B? The mass of the vapor. Oh, I haven't seen a mass in a long time. Right? Nasaan na? Right? Where is that going to be? So now this opens up the next part to our solution. Now we are going to have to, well, understand how much mass is in here in the first place. Right? How do we get there? Well, again, earlier we were saying that the mass of this thing remains constant. Okay, sure. Right? But, right? But, what is the mass? I don't know, right? But we do know the value or the relationship between big V, because there is a big V in here, and the small v. For us to turn a small letter into a big letter, we just have to say V is equal to m times small v. And as a result, your mass can be known for V over small v. And mind you, this does not change. And we just said earlier that this does not change. Therefore, the mass will also not change. Right? Therefore, also the mass will not change. Now, we will say that this is 0.5 meter cubed all over, if you remember, 0.8475 meter cubed per kilogram. And now, let me just center this. Now we will cancel, and we will be left indeed with a kilogram. That's in the denominator of the denominator. You can flip that to turn that into just kilogram. Right? Therefore, this value will be 0.58997. So for all intents and purposes, I suppose this will be 0.590 kilograms. Now, let's compute this using the orange value. Right? Let's compute this using the orange value. 0.5 over 0.847 instead of 0.8475 will give us, that is scary, it's giving us the same value, right? And that is the scary bit, right? The only thing is this comes from, this value comes from 5899705. So 1. And this next value comes from 0.590319. 3187, so 0.9. Right? That is small. The changes are small. So you can see how this approximation might work, but also that this approximation is scary, right? Just don't think about the fact that if you take the reciprocal, that will be infinity, right? Just take your mind off of that fact, right? Now, is this our answer for letter B? Why are they asking for the mass at state 1 and state 2? Because they're trying to ask the mass of the vapor, not just the total mass, right? Because we know that this water in here initially is already a mix of liquid water and water vapor. They just want to know how much water is water vapor for state 1 and how much water vapor is in state 2. How do you get there, right? Hopefully, we can harken this back to our topic 2, right? If you guys open your notes for topic 2, we will see that your mass total is just the sum of the mass of the liquid and the mass of the vapor portion. And hopefully, you also remember that the quality X is defined as the mass of the vapor or the gaseous phase over the total. Therefore, look, the mass of the gaseous phase or the vapor phase is just equal to X times mt. I just multiplied both sides by mt, right? The mass total. Wait, we have the mass total already, 0.590. And furthermore, we have your value of your quality at state 1. Oh, therefore, okay, that's it, right? For us to be able to get the value of the mass, the mass of the vapor at state 1, we just need to do x1 times m, which is going to be 0.5 times 0.590, right? Kilograms is equal to 0.5 times, or what is this again? 0.8475. That will give us a value of 0.294985. So 0.295, right? Kilograms. And I'm doing 3 decimal places because, well, it's 5. I'm not very comfortable telling that this is 0.30. And plus, I'm just giving you guys an idea, right? What the more exact kind of measurement would be. Because I ask you guys usually, oh, please just do this in terms of 2 decimal places, right? And now, what about for the mass of vapor at state 2, right? Therefore, this same thing should work, right? x2. But we don't have an x2 yet, but we can compute for x2. The thing is, we already know that your v2 is equal to vf plus x2 times vg minus vf. We have values, we just pulled values of vf and vg from the table. So check, 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 and actually check. Therefore, we can compute for the value of x2, right? If you rearrange this, right, you transpose and then you divide both sides by vg minus vf, you will have another formula for your quality. Quality here is just going to be your value minus the liquid part all over the gas part minus the liquid part. Right? And if we put all of this together, we're going to get 0.8475 minus 0.001058 all over 1.159 minus 0.001058. This will get us a value or a quality of 0.8475 minus 1.159. This will give us a quality of 0.7309. So 0.73098, the 7310. That is your quality for state 2. But now, let's try this. V minus VF over VG minus VF, wherein cancel because both of those are assumed to be 0. So 0.8475 over 1.159, right, should be what? Oh, wait, sorry. Our value of V is going to be different. 0.847 instead. Right? 0.847 instead. 0.1159. We will get. Okay, somehow it's going to be a bit different now. 0.7308. Right? So, but you can still see if you just talked about the the quality as a percentage, 73.1% and 73.08%. That's still very close, right? So now we know at the very least your value of, oops, what is happening? There you go. Now we know the value of your state 2 here, right? The mass pala, 0.7310 times 0.590 kilograms. That will be equal to 0.43129. 0.43129, or let's just say 0.431 kilograms. That is your value of MV at state 2. Now again, let's try this again. And let's try this again. 0.7318, 0.7308, 0.590. Let's just see the difference, huh? 0.431172. Yeah, there's not a lot of difference. It's still 0.431. So that just goes to show, huh? That just goes to show. This is still very convincing, right? This is still very convincing as an approximation. If ever you guys are working with liquid water, try this out. Maybe this can simplify a lot of your, what do you call this? Your calculation, right? Just don't worry about, 1 over 0 and everything, right? And now, finally, we have P3. P3, what was required of us again? If we were to continue the heating process until the sample is fully dry, how much pressure would the gauge read then? Fully dry. You can see that from state 1 to state 2, the quality is changed from 0.5 to 0.73. When will it become 1? Right? When will it become 1? Okay, that's interesting to think about. Right? State 3, if we were to create such a thing as state 3, right? If we continued heating, of course, it would accumulate more, right? V3, let's just fill this out actually. X1 is equal to 0.7310. And then your T2 in here would be 111.5. 0.4 degrees Celsius. And your V3 would still be 0.8475 meter cube per kilogram. And now your sorry, this should be X2. Your X3 in here should be 1, right? Because it's now a saturated vapor. What will the value of your pressure, what would that value be, right? And so let's just see. This V3 should be the VG for this to be 1, right? Because we are talking now about a saturated vapor, right? Right, so let's continue our solving here. Since X3 is 1, right? State 3 should be saturated vapor. Should be saturated vapor. Moreover, the value of V3, which is 0.8475, because we know it's a saturated vapor, needs to be VG, right? It should be the gaseous part na talaga, right? Everything should be water vapor at this point, VG, right? So let's search, right? Where will that VG be 0.8475? So let's continue searching. As you can see nga, the vapor, right? The VG continues to get lower and lower. So lower and lower, not here. Between these two values, there is your 0.8475, right? So that must mean the pressure should be somewhere within 2 bar to 2.5 bar, right? And so what else are we to do except for interpolation, right? Your pressure in bar is here, and then your what is this again? Your V in meter cube per kilogram is in here. So you have 2 bar and you have 2.5 bar. You don't know this value of P3. All that you know is in here in 2 bar it's going to be, oh sorry, this should be VG. Oops, should be VG. All you know is that for 2 bar it's 0.8857. 0.8857, and for 2.5 bar it will be 0.7187. All that we know is that this should be 0.8475 or 0.847 actually, right? Or 0.847. Let's just attach that in case, right? In case. Right now, how are we going to do this, right? Let's just mid minus small over big minus small, right? P3 minus small 2 over big minus small 2.5 minus 2 is equal to 0.8475, right? Minus small, don't even look at the value, right? Just look at the corresponding 0.8857 all over big minus small 0.7187 minus 0.8857. Right? Now, your value of P3 here, right? I will also shadow 0.847 in case, right? So you can do your shift solve here, right? You can do your shift solve here, or kailan ba? When will I meet you guys next? Basta whenever we have our next meeting, please let me know. Please remind me that there's something I'm supposed to teach you, right? This secret interpolation trick. I feel like some of you already know about it, but let's just shift solve for now. Let's just shift solve 0.8475 minus 0.8857, 0.7187 minus 0.8857. We shift solve and we get the value of x, or yeah, tama, x, which is your P3 is 2.11437 or 44 bar, or let's turn it into kPa this time, 211.44 kPa. We just slid the decimal place twice, right? And this will be your P3, right? Or in the case of our approximation, what we will get is, oh wow, 2.1159 bar. So as you can see, it's still very close, right? It's neck and neck. If anything, the errors only come two places after, right? So that's very small, very interesting, right? Those are our answers for number, what is this number? Number 8, right? So this is a lot, right? Because I explained every single detail, right? I explained every single detail. And again, if you guys are still unclear on something, please just let me know, okay? I'm the professor here, right? If you guys are gonna get pieces of information, it's probably gonna be from either a textbook that I've recommended or just from YouTube or from the horse's mouth, right? I am the horse. Okay? So ayun. Right? So let's just fill this out. Your P3. Oh no. Your P3 is 2.1144 bar. You guys go ahead. If you want to get the value of T3, be my guest. Right? So there you go. Those are our solutions for number 8. Hopefully, you also find the orange bits very interesting. You might want to try VF is equal to 0 next time, but please don't go crazy over it. Huh? The thing is, the value of the density of water is 1,000, which is a really big value. I cannot guarantee the same thing will happen for other substances. Like for example, let's just say, ayan, for refrigerant 22, I don't know what the value of density of that is, right? From here, it looks like it looks a bit big. And anyway, sige, right? I don't condone this for other substances. That sounds weird. I only can support this if you are dealing with liquid water, because liquid water is so small. Okay? Ayun. Right? I will end this now. I'll end this recording now because that has taken a lot of time, and I will record problem set 4 in a different video. Okay? So again, if you have any questions, please let me know. Thank you guys. I will see you next time.